an alpha particle with a charge of 2e, 2 electron charges. I think it's called an elementary charge. And a mass of 6.6 times 10 to the -24th. I'm going to assume kilograms because that sounds about right. Travels in a circular path, a radius 4.5 centimeters. We'll have to convert that to meters. A magnetic field of 1.2 Teslas. Calculate the speed of the alpha particle. Okay, so we have an alpha particle. We draw it as a dot, like so. Make a little alpha, so we're like, oh, that's an alpha particle. It's traveling this direction, but its path is going to be, it's supposed to be a circle. That's a terrible circle. There we go. Something kind of like so. But at this top point here, it's only going to be going this direction, because it's at the top of the circle, and it's going to feel a force going towards the center of the circle. This is what's going to give it its acceleration. That will be centripetal, circular. And so we want to find its speed. So what I'm going to start doing is write up so there's going to be a force, a centripetal force that's causing it to move in a circular motion. That centripetal force is going to be due to a charged particle moving inside a magnetic field. And the formula for that is going to be QV cross B. And these are also supposed to be vectors. The V cross B is going to be the velocity time across the magnetic field. And the cross product is a measure of how perpendicular two vectors are. So what happens is you get one vector crossed by another vector, and it's going to produce a third vector that is perpendicular to both the previous vectors, and the magnitude is going to be related to how perpendicular two vectors are. So specifically by sine of theta. So it's going to be the sine of the angle between the two vectors. So I'm going to draw the magnetic field up here. We don't actually need it, it's just assumed. But I'm going to say it's going into the board. Wait a second. V cross B. It's going to be coming out of the board. And that's going to create a force going down. It could be going into the board too. Same problem. I should not get caught up in the nuance. So then, force is also defined as mass times acceleration. I'm going to do a little subscript C here just to imply that this is centripetal acceleration. It's not needed, just helps me keep everything straight in life. I guess curved, exact opposite of, not important. You see where this is going. mv squared over r. And what I'm going to look at is now that I got these equalities written up, I have QVB, the force due to a charged particle moving in a magnetic field, and v squared over r, the force required for circular motion. So then I'm going to say QVB. I'm going to drop the cross product because we're just multiplying by sine of theta, where theta is the angle between the two vectors. They are perpendicular. Sine of theta is 1, therefore QVB. And then the vectors gives us direction. I'm not going to worry about the direction. I know it's going to be down. It's going to be mv squared over r. One of the v's cancels out. And what are we even looking for? I got so excited with solving things that okay, speed. I want speed. So solving for v, which is speed. V without the vector speed, v with the little vector hat, velocity. Because velocity is a vector, both magnitude and direction. So I'm going to call this QB radius over mass. And we probably want an actual answer for that, don't we? We can do that. We can totally do that. So this is going to be 2 times 1.602 times 10 to the negative 19th. That's the charge of an electron in coulombs. The 2 represents that we have 2 protons in our alpha particle. The magnetic field is 1.2. The radius is 4.5 times 10 to the negative second. 4.5 times 10 to the negative second. And we're going to divide that by the mass of the particle, which is 6.64 times 10 to the negative 24th. And I'm going to do some simplifying just because I can. 2 times 4.5 is 9 times 1.2. 10 to the negative 9th times 1.602 10 to the negative 19th and 10 to the negative 2nd is the same as 10 to the negative 21st because we just add the exponents. 6.64. Is it 6.64? I think it's 6.64. 6.64, yep. So we have 6.64. It's supposed to be a 6, even though it looks like a 4 times 10 to the negative 24th. 10 to the negative 24th is the same as 10 to the 24th up top. And 10 to the negative 21st on top is the same as 10 to the 21st on bottom. I know it doesn't matter, I just don't like negatives. I tend to be a fairly positive person in life. 10 to the 21st and 10 to the 24th, when you divide one exponent, 10 to the 24th divided by 10 to the 21st, it's going to be the same as 10 to the 24 minus 10 to the 21, which becomes 10 to the 3rd, which is the same as 1,000. So now I'm going to put this into a calculator. My calculator choice is Wolfram, though any calculator that you enjoy will work just as well. So 9 times 1.2 times 1.602 times 10 to the 3rd, which is 1,000, divided by 6.64, and I get an answer of 2606. 2606, and that's going to be in meters per second. One thing to check with this is whenever you get a speed of a particle that goes crazy fast and you don't have any intuitive feel for how fast that actually is to make sure that's less than the speed of light. The speed of light is 3 times 10 to the 8th meters per second, which is greater than the speed of our particle. Therefore, the particle doesn't, it's possible that our answer is correct. Whenever you start getting something that's 10 to the 7th or higher, you need to start being cautious because you should start using relativistic, and just the Newtonian throwing a ball projectile motion isn't going to be as applicable as you would like. All right, period of revolution. So period of revolution is just how long it takes to make one circle. And so we're going to draw a picture. We have our center here. We have our alpha particle moving around. It's a much better circle that time. So velocity equals distance divided by time. I remember that because my car goes in miles per hour. And rearranging this, t, which is going to be period. I'm going to use a big T there to represent period because it's the time for one revolution. It's going to be distance divided by velocity, which is 2 pi r, which is the circumference of a circle, over velocity, which I'm going to call v, 2 pi times r. The radius is, I know I should know this, 4.5 times 10 to the negative second. 4.5 times 10 to the negative second, all over 2606. And if I was a better person, I'd do some simplifying and do this in my head. I am not that good of a person. So this is going to be 2 times pi times 4.5 times 10 to the negative second divided by 2606, which gives us, drum roll, 1.085 times 10 to the negative fourth seconds. And that's going to be the period of revolution for our mystery particle. So we want to find the kinetic energy of this particle. And we specifically want to find the kinetic energy in electron volts. And so what I'm going to do here is I'm going to find it using 1/2 mv squared. And I feel confident that I can get away with this because it's moving relatively slow. By slow, I mean a small percentage of fraction of speed of light. So, because 2606 is much smaller than 3 times 10 to the 8th. So, let's see here. 1/2, that's just going to be 1/2. Excellent, go team. The mass is 6.64 times 10 to the negative 24th. 6.64 times 10 to the negative 24th. Times its velocity, which is 2606 squared. Okay, back to the calculator. We'll do 0.5 times 6.64 times 10 to the negative 24th times 2606 squared. Yep, that looks about right. Yep, and that gives us an answer that feels about right. which is 2.255 times 10 to the negative 17th, but this is in joules. To convert joules to electron volts, we have 1.602 times 10 to the negative 19th. That's the charge of an electron. Joules per electron volt. So we're going to get a much bigger number here because we're dividing by a very small number. 1.602 times 10 to the negative 19th. Ooh, this is actually going to have a lot of energy, which makes sense. Alpha particles tend to be fairly energetic. 140.7 electron volts. I guess that's not that much energy. That seems reasonable. So let's see, kinetic energy in electron volts. Bam, excellent, got it. So now the potential difference, which I had to accelerate to achieve this energy. Okay, so now I'm going to continue on with this picture here. So I'm going to redraw our starting picture. So basically what's kind of happened here is we have, let's say, an alpha particle. So we're going to have a positive plate over here. We're going to have a negative plate over here. And let's see, it probably asked for the electric potential. The potential difference, yep. Specifically, that's the voltage. What's the voltage? And so we have an alpha particle comes out here, moves in a circle under a magnetic field. So alpha particle starts here. It's repelled by the positive, attracted the negatives, goes through this little hole we have here, and then starts spinning because in this region we're going to have a magnetic field. And so to find, and so the question is basically, what is the voltage of the battery? We're not going to actually use a battery. That we'd have to charge up these plates to transfer the energy to the alpha particle. And to do that, we're going to use potential energy, sometimes written as big U, is Q. I'm going to write this as delta V. Voltage is always a difference, so the delta is kind of redundant, but I like to put it there anyway just to remind myself. So delta V, our voltage, is going to be the potential energy over the charge. The potential energy is going to be the same as kinetic because over here, when the alpha is right next to the positive plate, it's going to be at rest, and that is going to have a lot of potential energy, which as it gets moving and it gets over to this over here, its potential energy is going to be 0, but all that potential energy is converted to kinetic, which is going to cause the spinning motion once it gets to the other side. So it's like throwing a ball up in the air, except instead of a ball you have an alpha particle. Instead of gravity doing this work, we have our charged plates. Charged plates which have an electric potential of voltage. All right, so we have 140.7 electron volts. Now this is one of the nice things about physics. Like, I complain about units in physics all the time, but this is one of the instances where it was done correctly. So the charge is going to be 2 elementary charges, 2e for the particle right here. And so then to solve this, we just cancel. The e's cancel. Usually you can't, it's not considered kosher to really cancel parts of a unit, but with electron volts, this works great, and it can totally be done. So we're going to have 70, I'm going to say 70.35. So it's just 140.7 divided by 2. And we're going to be left with volts. So that is the electric potential through which we have to accelerate an alpha particle to get it moving at 2,606 meters per second, which will then create a circle of 4.5 centimeters radius if exposed to a magnetic field of 1.2 Teslas. So that's how this problem works. That's the idea behind it. Hope that helped. See you next time.